All right, this topic is on graphs of functions. To graph a function, we want to make sure you have a complete graph that shows the basic shape of the graph, important points on the graph, and suggests that the graph has the unshown portions. We want to make sure you have the turning points where there is a local max or minimum. To find the number of the turning points, it is the degree number minus 1. The number of solutions or zeros always are going to equal the degree, and they're going to be real or imaginary. Example 1. Identify the degree, the number of solutions, and the number of turning points. Then you'll use a graphing calculator to sketch the graph. So number 1, A, y equals 2x minus 5. So this is going to have a degree of 1. So there's the degree of 1. So it's going to be a degree of 1. So this is what we call a linear function. It's going to create a line. The number of solutions it's going to have is going to be how many x-intercepts it has, which if we go back up to our list, the number of solutions or zeros will always equal its degree. So since the degree is 1, it'll have 1 x-intercept. The number of turning points is always 1 less than the degree. So since the degree is 1, so 1 minus 0, or 1 minus 1, excuse me. So we'll have 0 turning points. So then what we would do is we would take out our graphing calculator and we would type this into the graphing calculator, and it will look something like this. It'll have a y-intercept of 0, negative 5, and then an x-intercept right here at 2.5, comma 0. That's 2.5, comma 0. The second one, y equals 1/2 x squared. Now our degree is 2. So now our solutions, our 0 is going to increase by 1. And then our turning points, so 2 minus 1 will be 1 turning point. So we would type this into the graphing calculator. This will be the shape of what we call our parabola. I'm going to label a few points here. So we have the vertex at 0, 0, 2, comma 2, and then negative 2, comma 2. And this right here is the turning point. All right, the next one. Now our degree is increasing to 3. The number of turning points is 2. I'm going to go ahead and graph it. Now, this is what we call a cubic. 0, 0, 2, comma 8, negative 2, negative 8. And again, this one's only going to have 1 x-intercept right there. And this one's going to have 1 x-intercept right there. one x-intercept right there. And these are what we call the solutions are the zeros or x-intercepts. The turning points, you can have up to 2 of them. In this case, this is kind of a goofy looking turning point here on that last one. All right. Example 2, identify the degree of the number of solutions, the number of turning points for this function. Step 1, you want to go ahead and use Zoom 6, which is the standard window, and look at the graph. So go ahead and type that into the calculator and then choose Zoom 6, the standard window. Step 2, you want to change your window then to now -1010 and -2510 and look at the difference in the graph. Which one gives you the better view? All right, so now if we look at it, see how when we zoomed out, it did show a better fit of our cubic function. When we were at the smaller, well, remember the standard viewing window is -1010, -1010. That's the standard. It doesn't give us all of the ordered pairs. So I'm just going to give you a couple ordered pairs here. Here's 0, -13, and then 2, -17. And again, this is the better view, is that second one. And then these are the turning points. The local minimum is here, and then the local maximum is there. Those are the turning points. Example 3, use your graphing calculator to graph this function. This is what we call a quadratic function. For the x values between -60 and 60. That should say 60. So we want to find the appropriate window for y. So we want to find this y values to make it appropriate. So we're going to go ahead and type this into our graphing calculator. And when we're done, what will be appropriate is to make that y out to -900 and then 500. So you want to adjust that scale out so that you can get this local minimum right here, -30, comma, -870, which will be the local minimum, which we can also call that the vertex of the parabola. Okay, example 4, use the table below to answer the following questions. So now this is going to be a discrete function. It's going to be listing off a table of values. So how you do that is you would follow these steps and make sure you have your window. You would enter the data points. This is going to be list 1. This will be list 2. And you would graph the ordered pairs. And what your graph should look like when it's done is something like this. Then, in part B, you would then graph y equals 5x minus 15 and see if you get those points to fall on the same line. Now, do the points fall on the same line? Yes, they do. Those points in the green fall on that function. Example 5. Suppose that the cost of removing P percentage of population from drinking water is given by this model. C equals 5,350 P divided by 100 minus P dollars. And what we want to do first is use the restrictions of P to determine the limitations on the horizontal axes. So the x-axis is going to represent the P, or the pollution percentage. The y-axis is going to represent the cost. In dollars for that removal. And I'm going to go ahead and change this equation to just y equals 5,350 x over 100 minus x. Because that's what you're going to be typing into the graphing calculator. And we want to do first is, what are going to be the restrictions for P on the horizontal axes? So think about, can you have a negative amount of population percentage or pollution percentage? No. So this is going to have to start right here at 0. So the pollution can't be a negative number. So pollution can't be a negative number. Now we're going to go again, graph on the viewing window. Why is it reasonable to graph this function on that window where we want the cost to also be greater than or equal to 0? Well, cost can also not be a negative number. We can't have negative dollar amount. Negative money doesn't exist. All right, so when we graph it, with that window, it looks something like this. Part C, find the point on the graph that corresponds to P equaling 90. So here is 90 somewhere over here. We want to find out what that number is, and then interpret what that P represents. So think about x is the same thing as P. And what is that number? So you can use your graphing calculator, and there's a table of values with the graphing calculator. So you go to second table, and you can find 90 in that list. So, and you would see then that y will equal 48,150. So what does that mean? When the pollution is at 90%, the cost of removing it will be $48,150.